This UCSD TV program is a presentation of University of California Television for educational and non-commercial use only.
January 1994, Northridge, California. For anyone that remembers that day, the images are frozen in memory. This powerful quake struck one of the most densely populated regions of North America, yet less than 100 people perished. While modern engineering did much to minimize the loss of life, lessons are always learned from natural disasters of this magnitude. One of the lessons learned was found in many steel buildings where over 100 fractures were discovered in beam-to-column welded connections. While none of these buildings experienced collapse, codes for steel construction were revised to prevent the types of damage revealed in typical mid- and high-rise buildings. Another common type of steel construction is low-rise metal buildings. These structures use tapered steel members and bolted connections that performed very well in the Northridge and other severe seismic events. However, the code revisions as a result of the Northridge event did not completely address intrinsic design differences of these lightweight, low-rise structures. Current code requirements that apply to the use of steel in frames assumes that deformation and subsequently localized damage where the energy from the earthquake is absorbed will occur near these beam-to-column connections. This is something called the plastic hinge location. Greg Dearline of Stanford University comments on the effect that these different design approaches have on the formation of the plastic hinge.
Typical steel frame buildings will have what we call plastic hinges occur next to the columns in the beams. In these metal buildings with tapered members, their economy is due to their lightness, and in fact we might not see the plastic hinges that we see in conventional steel frame construction, but instead we see distributed yielding, distributed distortion. And again, those are things that are really not recognized in current building codes.
Therefore, the Metal Building Manufacturers Association and the American Iron and Steel Institute partnered with UC San Diego and the Network for Earthquake Engineering Simulation to conduct tests to verify designs and performance of metal buildings and advance the understanding of structural performance as a whole. Lee Shoemaker, Director of Research and Engineering for the MBMA, explains.
Well, MBMA is a trade association, and it was founded back in 1956 by 13 metal building manufacturers. Their mission was at that time, and still is, to advance the collective interests of the metal building industry. And there's always been a focus on technical and engineering activity, and the goal there is just to make sure metal buildings perform well. We also want to minimize the materials that go into the building, primarily steel, so we design this as efficiently as possible to safely carry loads.
Jerry Hatch, chair of the MBMA Technical Committee, comments on why this testing program is important.
With our tapered member design, that zone of damage or energy dissipation moves away from the column. And one reason we're doing this testing is to confirm our thoughts that that is happening, and when it does move, where does it go? Our predictions of behavior of these buildings is only as good as our understanding. And testing is where we come to understand the limits of use for these buildings. And so being able to see what it can do is invaluable in coming up with credible technology and putting together good design limits that can be used by the engineer on a day-to-day basis.
One of the contributing metal building design engineers, Scott Russell, comments on some of the test program's goals.
What we hope to do with this is to make sure that, number one, that the code addresses our type of product correctly, so that there isn't any type of failure out in the marketplace that is unanticipated. And only research like this will allow us to do that. And secondly, we'd like to be able to put the steel where the steel is actually needed as opposed to where the building code currently requires it.
Greg Dearline comments on the ultimate purpose of the test program.
Again, the purpose of this whole research project is to understand these buildings, to write building code provisions that are tailored to these metal buildings, as distinct, which are made of steel, as distinct from other steel-framed, more conventional tiered building construction.
One of the distinct qualities of these lightweight metal buildings is the use of innovative strategies for seismic resistance. Two of the research program's advisors comment on these strategies.
During an earthquake, we have a kind of a motto that when we design for gravity loads, kind of when in doubt, make it stout works well. But that same philosophy does not work so well when we try to design structures to resist earthquakes.
One of the basic concepts of how we try to get a building to survive an earthquake without collapse is by building in what we call ductility, and another way to maybe look at that is energy absorption. So we try to have our buildings absorb the energy of an earthquake. And so we try to survive the earthquake not by making the building very strong, but by making it very energy absorbent. We built in what I would like to call crumple zones, areas that will absorb the energy of the earthquake and allow the rest of the building to remain standing, with the ultimate goal that we don't want the building to collapse so we can save lives.
The tests will be conducted at the Engelkirk Structural Engineering Center's Nice UCSD Shake Table, the largest and only of its kind in North America. The testing will be supervised by Professor Chiaming Wang and his graduate student, Matt Smith. This comprehensive testing program will use 3 different specimens to test different design parameters. While the specimens are large enough to be buildings on their own, some 20 by 60 by 20 feet high, they only represent a section, or bay, of what could be much larger buildings. The first specimen will represent a common, archetypical, single-story, lightweight metal building. The second specimen will represent a metal building with tilt-up concrete walls. The mass of the walls, more than 10 times heavier than the entire metal framing, creates substantial forces on the structure during an earthquake. The third and most complicated specimen will represent a structure with a mezzanine or second level. Current codes do not adequately address this design. This configuration presents complex loads with the weight of the mezzanine in the middle of the columns and heavy tilt-up wall loads at the other end. Like other tests conducted at the Engelkirk Structural Engineering Center, the metal building specimens are built onto the table that will reproduce the earthquake motions. Each specimen is thoroughly instrumented with a variety of sensors to measure strain, displacements, and accelerations that will describe how the structure is behaving under the influence of the seismic loading. Each test is derived from an actual seismic event: the Chi-Chi earthquake in Taiwan, the Landers, Loma Prieta, and Northridge earthquakes. And finally, the design basis and maximum considered earthquakes are derived from the magnitude 6.5 Imperial Valley earthquake of 1979. A design basis earthquake, or DBE, is an earthquake record to which codes require structures to be designed. A design basis earthquake happens an average of once every 475 years, and a building that endures a design basis earthquake might suffer some damage, but can be repaired and reused. A maximum considered earthquake, or MCE, is an extremely rare event that statistically won't happen but once in 2,500 years. It is 50% more powerful than the design basis earthquake. The goal of the building codes and the structural engineer is to produce a building design that can withstand a maximum considered earthquake without collapse. It may be severely damaged and ultimately condemned, but it will have maintained life safety of the occupants. The first tests will be small and will increase in intensity each round, starting at 25% of design basis and increasing to 50, 100, 150%, and beyond. For the first specimen, it is time to apply the design basis record. This will reproduce the earthquake motions of the magnitude 6.5 Imperial Valley earthquake of 1979. The structure performs well, showing how the steel frame works to absorb and dissipate the forces created by the earthquake motions. The team reacts to viewing the structure's performance.
We just ran the 100% of a design basis earthquake, and the building did great. We're anxious to see tomorrow the higher level shaking to see at what point it might fail. But so far, so good.
It is the reason that I am an engineer, is to see these types of things in action, and it's nice to be able to simulate this in a facility like this.
We've sponsored a lot of research to get a theoretical handle on the behavior of these types of structures, and to see how they actually perform is really encouraging.
The team prepares to subject the structure to 150% of the motions of the original quake. This is a maximum considered earthquake, a quake that isn't likely to occur in 2,500 years.
50%. Roger.
The team looks on with concern. The structure has shown some kind of failure. Or has it? The team finds that the failure was not in the structure, but the test apparatus.
These are the anchor rods that we had. This is actually an A36 threaded rod. They were fillet welded around. There were 4 of them going through each base plate. And it appears that they all just sheared directly off. That's not going to invalidate our results, because this is a problem with our support system that we developed. It's not an actual problem with the frame itself. This motion that failed this was significantly higher than anyone should ever reasonably expect to go through. Again, that shows us that our building is still fine. So this is a good structure. We're going to take this plate and attach it to these protruding plates on the base. We're going to do this on each side of each column and just weld these down.
With the anchors repaired, the team presses on. Will the structure survive a quake twice as big as the original event?
Imperial Valley, 200%. Running.
The shake is phenomenal, an event that is not likely to occur in anyone's lifetime. But the researchers and engineers are not satisfied. So the team continues with a quake record 2.5 times more intense and extreme than the original quake. Finally, the team has precipitated a failure. A localized buckle forms near the predicted location, away from the actual beam to column connection.
Wow, the failure is right up there.
Though there is failure, the structure is intact and far from a collapsed state.
We may just to see what else happens. We've done that in the past on previous tests. We've gone farther just to see where other type failures occur. So It'll all depend on what these two think we should do. It's pretty exciting stuff, huh? It moved pretty good.
Oh, we still have a stable system, if that's the only hinge.
Yeah, let's go to 300.
300?
Probably, I think that's about the last test.
I'm sure. Officially, according to our building codes, that's a failure. But the building is still standing, so we don't have a collapse. We're going to go up to a 300% design basis earthquake and run it again. I expect that we're going to get an actual collapse.
Once again, the ability of steel to absorb large amounts of energy is evident. The beams buckle and distort under the extraordinary loading, dissipating energy throughout the structure. But even with previously failed beams, the structure remains standing. Only after the phenomenal forces of a record 3 times more intense than the original quake can the team precipitate fractures.
Because it's so much like this.
They occur close to where the researchers' models had predicted, verifying many design parameters. Yet even with this damage, the structure remains standing and safe. For this specimen, testing is finished. As it went through the many tests, this first specimen clearly revealed the importance of designing for energy dissipation and the durability of these lightweight metal buildings. The next specimen represents a popular design that is widely used in structures like large superstores, warehouses, or office buildings. In this specimen, a lightweight metal building frame supports precast concrete walls 10 times heavier than the supporting structure itself, which in turn creates greater forces on the structure during an earthquake. Seismic design expert Tom Sable, another advisor to the project, comments on the forces created during an earthquake and what might be the expected effects on this specimen.
Earthquake loads are what we call inertial loads. And what that means is that when the ground moves, the building itself wants to remain stationary. But it can't because it's connected to the ground. So eventually it tries to catch up with the ground, which then has moved in the opposite direction. And so the building is always playing catch up because of these, the ground motion and the inertial loads. In this case, the concrete panels represent a very large inertial load. And so what we expect to see is that the loading that's generated by the building and its response to the ground motion will be transferred into the steel frame. The kind of behavior that we would expect to see in this would be flexing of the steel as the structure moves back and forth during the earthquake. And when it's loaded to its highest levels, what we expect to begin to see are local failures. And these local failures are not so much along the lines that the structure collapses, but what we see are examples of steel plates beginning to buckle, bend, and that will begin to have a consequence and an impact on the performance of the structure overall.
The test sequence begins. The design basis record is applied. This is a quake that doesn't happen but once in 475 years. The dynamics created by the heavy wall loads are clearly evident. As predicted, the intense loads cause a buckle in the roof beam, but the structure remains intact. While the structure remains intact and safe, this earthquake is clearly an event one would find intimidating. The test ends. Graduate researcher Matt Smith reports on results of this first test.
The rafter buckled in the same place that the first specimen buckled, in pretty much the same fashion. It's exactly what I expected. My prediction came from a numerical model and checking limit states just through the code equations, and they seem to be accurate.
The team presses on with the maximum considered earthquake record. The structure heaves and bends under the enormous loads of over 55 tons of concrete. The test ends, and the team inspects.
Pinch point, you see? No, the flange is fractured.
Oh, fracture there, about half of the width of the bottom flange on this side.
Once again, the predictions were accurate, and the beam buckling increased due to the intensity of the maximum considered earthquake. And still, the structure remains intact and safe. A principal contributor to the test program, Don White, who helped develop design guidelines for tapered structural members used in lightweight metal buildings, comments on the test results.
The test that we saw today, the building performed extraordinarily well. With all that weight that the structure was supporting laterally during the earthquake, there was a good chance that the building may not respond very well. Many of us that came here today thought that the building may not actually be able to reach the design level earthquake, but they were able to take the building up essentially to well beyond the design level earthquake, and the building, the integrity of the building still largely remained intact. The failure mode that we had happen in the frame today, that was expected. The inside flange or bottom flange of the roof girder, it was moving in and out of the plane of the frame quite a bit. We started to see buckles forming in the flanges, but the overall integrity of the system stayed in there.
Yeah, we've accomplished what we now do. We want to see what happens.
But the team wants to know how much force would be needed to precipitate an actual collapse. So the researchers subject the damaged structure to a static test, using load cells to load the structure both vertically and horizontally, forces that the structure is subjected to in a seismic event. Even with the beams already compromised from the earlier tests, the team needed to apply 40,000 pounds of force to deform the structure, and still, the structure remained upright and did not collapse. The structure is dismantled, and the final, perhaps most complex specimen is readied. This specimen has both a heavy concrete wall at one end and a mezzanine or interior second floor level. The designer explains what is being explored with this specimen and why.
From this particular test, we are hoping to learn more about the interaction between the mezzanine and the frame, how the big weight located at the mid-height of the column will affect the overall frame behavior. We have really two levels where the forces are, because on one side of the specimen is the mezzanine, on the other side we have the heavy structural wall. So the force will be actually at two levels. Because of the weight of the mezzanine, the structure might behave differently. That big mass can change the behavior of the frame. So it's different than what the codes would tell, and hopefully after this research we'll be able to propose some new language for the building codes, what to do with mezzanines and how to handle mezzanines within our type of structures.
The team is ready to test the structure with the design basis earthquake.
Running.
The structure survives admirably. The researchers inspect, paying particular attention to the panel zones, where lateral loading is concentrated in the frame. The researchers press on with the maximum considered earthquake, a record that is 50% more intense than the design basis earthquake. The motions and forces applied to the structure are phenomenal, those of an earthquake that won't occur in 2,500 years. the structure remains intact. But after this maximum considered earthquake test, the team observes that buckling has become apparent in the panel zones, the area where the beams meet the columns. This is a different location where this particular frame has dissipated the earthquake's energy. After inspection, the team moves on with an even more intense test, a quake twice as strong, or 200% of the design basis.
Imperial Valley, 200%. Running.
Again, the structure remains upright and safe. The buckling at the panel zones has increased, but the researchers want to explore the extremes of structural performance. After inspection and discussion, the team presses on with a record 250% more intense than the original quake.
Imperial Valley, 250%. Running.
The deformations at the panel zones increase, the intense forces causing them to distort as the structure absorbs and distributes the energy of the quake motions throughout the frame. The panels endure repeated cycles of severe deformation, yet the well-designed structure remains intact despite the phenomenal intensity of the quake motions. The test is complete. The researchers find that considerable deformation occurred in the beam-to-column joints. The web deformed and torn from absorbing the severe loads of the phenomenal quake record.
Significant rupture, very long rips, and we see daylight through the steel.
Despite the substantial failures in the panel zones, the structure remains intact. Innovative, careful design has prevailed again. Jerry Hatch, chair of the MBMA Technical Committee, had some final thoughts on the success of the test program.
The tests have exceeded our expectations. To survive a 2,500-year earthquake without collapse is the intent of the code, and our buildings have been doing that, and so we've been very pleased with the results of the tests.
Those results have not only clearly shown the ability of metal buildings to endure severe seismic loading, they have provided a wealth of data to validate computer models, so researchers, engineers, and designers can further investigate metal building design and take full advantage of these unique structures to take metal building technology into the future.